The atmosphere of the Earth is a thin layer of gases that, because of the gravity of the Earth, are held close to the surface. Now, because the gravity is pulling it towards the surface, the thickest part of the atmosphere is right near the surface. If you were to move up higher and higher into the atmosphere, you would see that the molecules would spread out more and more the higher you go. So the density is always highest near the surface and then decreases with altitude. Let me show you a good demonstration of how this is the case. If you were to move up 5.5 kilometers, about 3.5 miles, you would be on top of half of the atmosphere. But instead of going another 3.5 miles to be on top of the whole atmosphere, the density is much lower, meaning the molecules are much more spread out. If you were to double the height, you would only be on top of 75% of the atmosphere. In fact, to get on top of 99% of the atmosphere, you have to go up about 20 miles to reach, to be on top of 90% of the atmosphere. The atmosphere is made primarily of nitrogen. One of the reasons this is the case is that nitrogen is made of N2, two nitrogen molecules, which, remember from our chemistry, you would have covalent bonds bonding the nitrogen. With nitrogen, we have a triple bond, 3 covalent bonds between the nitrogen. That's a very, very stable atom, and so it's hard to get rid of. Therefore, about 78% of our atmosphere is nitrogen, and only about 21% is oxygen. Now, this is a really good thing because oxygen is quite flammable. If our atmosphere were 100% oxygen, light one single match and boom, the atmosphere is gone. Have one simple spark and the atmosphere would be gone. So we are very, very grateful for the 78% nitrogen that's in our atmosphere. In addition to nitrogen and oxygen, the third most prevalent element in our atmosphere is actually argon. Argon is a very inert gas and so is not harmful to our health. In addition to these 3 molecules, we have a ton of trace elements. The most abundant of these is water. Water is probably next to oxygen, the most important compound in the atmosphere, and we'll see that in a later video. Water can take up anywhere between a fraction of a percent of the atmosphere and 4% of the atmosphere. So that varies. Other compounds in the atmosphere include carbon dioxide, neon, helium, krypton, many, many others. In addition to actual molecules, there are also what we call aerosols, or just small particles that are so small they are suspended in the atmosphere. Things like dust, smoke, salt, and then some liquids are also suspended up in the atmosphere. Now, to talk about the effects of the atmosphere on us at the surface, we need to talk about atmospheric pressure. Now, pressure would be how hard a force is applied to a surface. So the atmospheric pressure results from the weight of the atmosphere pushing down on the surface of the atmosphere. In other words, pushing down on us. So it's a direct result of Earth's gravity that we feel pressure from the Earth. Now, if you were to start outside out in outer space and move towards the surface, since you'd have more and more atmosphere on top of you, you would see more, feel more pressure. So if we have the atmosphere looks something like this, the density decreases with altitude. At this point, and let me draw it this way. At this height, you would only have a small amount of atmosphere on top of you, so the pressure would be quite light. A little bit further down, pressure would be a little bit higher because you have more molecules pushing down on top of you. Further down you go, the more and more molecules are on top of you until at the surface of the Earth, you've got the entire atmosphere pushing down on your shoulders. That's where you're going to feel the greatest pressure. Very similar to diving underneath water and the pressure getting higher and higher as you get deeper because you have more water pushing down on top of you. That's what we call the hydrostatic view of atmospheric pressure. There's also the molecular view of atmospheric pressure, which is that pressure is basically a result of the number of molecules and the force with which they strike a surface. The further down into the atmosphere you get, closer to the surface, the denser it is, so the more molecules you have to strike the surface of the Earth. So your pressure is going to be much higher at the lower altitudes. Now, here's a really simple device to measure atmospheric pressure. It's what we call a barometer. Now, excuse me, mercury is a great substance for this. Mercury responds very, very well to atmospheric pressure. Basically, what let me tell you a random little thing here before I show you the barometer. When you have a cup of soda or a beverage of some sort with a straw, you have the atmosphere pushing down on both the fluid within the straw as well as on the fluid around the straw. Well, how do you get the fluid up through the straw into your mouth? Well, you suck on it. Basically, what you're doing is you are eliminating that pressure pushing down through the straw. And so the atmosphere is pushing on your drink down here, which will then push the liquid up through the straw, and then it'll go up into your mouth because the atmosphere is pushing down on the drink, and the only place for the drink to go is up through the straw. Now, a barometer acts in a very similar way. You have a tube that has a vacuum, which is the absence of air, or in other words, there's no pressure inside of that vacuum. But the atmosphere is pushing down on a dish of mercury outside. So the only place for that mercury to go is up the tube. In fact, if it is a true vacuum up in this tube, then the mercury will rise 76 centimeters into that tube, or 29.92 inches. And so when the mercury is at this level, we would say that the pressure is 76, not 76. We would use millimeters. Let me rewrite this as 760 millimeters of mercury. Or we would write that, since it's 29.92 inches, 29.92 inches of mercury. These are the exact same thing, just using different numbers. This is one standard atmosphere of pressure. In other words, here in Daytona Beach, Florida, this is the pressure we normally feel since we are at sea level. The pressure will vary day to day and during the time of the day. The variation is largest near sea level. The higher up into the atmosphere you go, the less the pressure is going to vary over time. Now, how does the atmosphere retain its heat? For example, if you were to go to the surface of the moon, daytime temperatures would be well over 200 degrees Fahrenheit, and nighttime temperatures would be well around minus 150 Fahrenheit. The Earth would be doing exactly the same thing as the moon, but we have the atmosphere. If we look at the incoming solar radiation, sunlight, coming into the Earth, as the sunlight's coming in, about 30% of the sunlight is going to either be reflected or scattered by the atmosphere or reflected by the surface itself. So that's about 30%. So we have another 70% that we need to account for. Well, some of that's going to be absorbed by clouds, some of it's going to be absorbed by air, and 51% of it is going to be absorbed by the surface of the Earth itself. If it's absorbed by the clouds or absorbed by the air, then that's what we call direct heating. We are directly heating up the atmosphere itself. But the 51% that hits the surface, that's going to indirectly heat the atmosphere. Basically, the surface of the Earth is going to absorb the solar radiation, then re-emit that energy as infrared radiation into the atmosphere. Well, there are certain elements inside of the atmosphere that love to absorb infrared radiation. This includes water, carbon dioxide, methane, and a few other gases. This process where sunlight comes in is absorbed and then re-emitted as infrared radiation, which is trapped by the atmosphere, is called the greenhouse effect. Now, let's take a quick look at what the atmosphere looks like. Normally, if you were to hop in a hot air balloon and move upwards into the atmosphere, what you would see is that the temperature, which is indicated by the x-axis in this figure, will actually decrease as you get up in higher altitudes, indicated by the y-axis. So higher altitudes means lower temperatures. This is normally what happens in the atmosphere. This has to do with the fact that the ground is most efficient at absorbing energy and heating up, and the atmosphere, the air, is not very efficient at heating up. So close to the surface of the Earth, what you would see is that the temperature would drop about 6.5 degrees Celsius for every kilometer or 1,000 meters of altitude. Now, this would translate in units that we use here more often to about 3.5 degrees Fahrenheit per 1,000 feet. That's not the number you need to remember. I would remember the 6.5 degrees Celsius per kilometer. That's what the atmosphere usually does. But every once in a while, you get what's called an inversion layer. What happens with an inversion layer is you have a layer of hot air that traps a layer of cold air underneath. The cold air will stay closer to the surface, layer of hot air above that. That's backwards from normal because then temperature would be increasing with height. And so that is what we call an inversion. Now, let's take a quick look at the entire atmosphere. Near the surface of the Earth, we have what's called the troposphere. This is the layer where temperature decreases with height, very normal, and this is also the layer where we see most of our weather. There are a few things that happen above the troposphere, but the stuff that affects us all happens here in the lowest 10 kilometers of the atmosphere. The layer above that is called the stratosphere. This is an inversion layer because the temperature increases with altitude. The higher altitudes are warmer and the lower altitudes are colder. That makes this a rather stable and calm, less turbulent layer. The reason for this is right in the middle of the stratosphere, you have a great big huge pocket of ozone, O3, also known as the ozone layer, which absorbs lots of ultraviolet radiation. And by absorbing that ultraviolet radiation, it heats up thus giving us the higher temperatures at the higher altitudes. Above the stratosphere, you have the mesosphere, where again you return to the typical normal decrease in temperature with altitude. The top layer of the atmosphere is the thermosphere. Basically, any molecules in the thermosphere are exposed to direct sunlight, and so they heat up very, very quickly. They're very, very energetic. However, these molecules are so far apart, you wouldn't really feel it. You would still feel cold because the molecules are so far apart. Once you get past the thermosphere, you have what is called the exosphere. That's where the atmosphere essentially is gone and becomes the vacuum of space.